back for lecture 3 in chapter 7. And I've said chapter 6 a number of times, and it is most definitely chapter 7. All right, so we got done. We were looking at how many electrons an atom has, and we looked at electron configuration, and we're going to go on with that. So the next thing we can kind of look at is we know that atoms can become ions. If you take a nice simple atom like sodium, sodium has electron configuration 1s2, 2s2, 2p6, 3s1. And now before we'd drawn the shell model for sodium. There's the nucleus, and it's time to kind of make some things right here. So sodium has 3 shells, and this is if we drew this with the old-fashioned Bohr model of the atom. And we know that we have 11 electrons. By the way, I don't know if you noticed this, if you counted electrons, 1, 2, 3, 4, plus 6 is 10, 11, you end up with the number of electrons sodium has. But sodium would have 2 electrons in the first, and then watch this. There's our first shell, and it's represented by the number 1 that's up here. So the second shell, this shell here, is represented by everything that has a 2 in front of it. Now remember, how many electrons can the second shell hold? It could hold 8. How many electrons does sodium have in the second shell? It would have had 8. Okay, now if you notice, out of all of our S and P's and D's, there's none of these that hold exactly 8 electrons, unless we come up with by adding some of these together. S plus D plus D, which one of these combined together could get you a maximum of 8 electrons? If you erase the D and added S's and P's together, you were correct. You end up with 8. And in fact, if you look at our 2s and 2p, if you add the number of electrons that are combined in there, 2 plus 6, you get 8. So watch this. The modern model of the atom looks like this. There is definitely 8 electrons in this second shell, but 2 of them belongs to the 2s, and the other 1, 2, 3, 4, 5, 6 belong to the 2p. So I don't have a good way of drawing that other than erasing this line and then adding in extra lines. The 2s electrons are here, and the 2p electrons are down there. All right? Okay, good. So we know where the 2s and the 2p electrons are. Then the last electron here is the 3s. I'm just going to kind of put this out here. And I know this doesn't look visually appealing at this point, but it kind of has a way of rectifying the modern model of where electrons are in atoms in all of these different orbitals versus the old model, the Bohr model of the atom. Okay, so let me get rid of my arrows, and we're going to look at what happens when sodium becomes an ion. Okay, during the break, I erased all the lines up here, and I redrew the Bohr model of the atom the traditional way. All right, so we know that sodium, based on its position in the periodic table, sodium over here in the periodic table is right beneath lithium, which is beneath hydrogen. So sodium is in group 1 of the periodic table. Now that has very special meaning, because any atom in group 1, if you remember our periodic table card periodic table card activity, sodium and any atom in group 1 had to have 1 and only 1 valence electron. Well, here's all the electrons in all the positions for sodiums. For which one of these electrons is going to be the valence electron? Well, here's the key. For any time you want to look at electron configuration and find valence electrons are always the outermost s and p orbitals. Now, if it doesn't have a p, it's just s. So where are the outermost? The outermost is the 3. And there's no 3p or anything, so I can't count these as valence electrons. So right now, this is my valence electron. And look, it works. Sodium is in group 1. It has 1 valence electron. There it is. This is the 1 valence electron for sodium. Okay, good. So what happens when a nice atom like sodium comes in contact with a nonmetal atom like fluorine? So let me pause for a minute and draw fluorine. Okay, so we talked about this a lot. What happens when an atom like sodium comes in contact with an atom like fluorine? And this is the Bohr diagram for fluorine. It's got 7 valence electrons, so it's missing a valence electron right there. And here's its electron configuration. Now, where is fluorine on the periodic table? Fluorine is all the way over here. Fluorine is in group 7, so how many valence electrons should fluorine have? Yeah, it should have 7 valence electrons. So where are they? Where are my 7 valence electrons? Now, if you remember, valence electrons are always the outermost s and p. So here it is. This is the stuff on the outside. I've got a 2p and a 2s. Well, there it is. Those are going to be my 7 valence electrons for sodium. Sorry, for fluorine. So 2s is 2 here and 5 there. There's 7. Okay? So we all know what happens. This is sodium is a metal and fluorine is a nonmetal. And we said that when a metal comes in contact with a nonmetal, it's going to transfer valence electrons. In fact, we know where this is going. This electron is going to get transferred to there. So that is our nice transfer, which is going to occur. Now, if this electron is gone, and this electron is now here. I'm going to draw it in here in blue. How does that change the electron configuration for sodium? What's the new electron configuration if this electron is now gone? Well, what's the electron configuration that's left? So left over, let me get rid of Bohr. Left over, when sodium has become an ion, is the electrons that's left right here, 1s, 2s, and the 2p. 1s2, 2s2, 2p6. This is the electron configuration for sodium as an ion. And we know it becomes the Na plus 1 ion because it has lost this negative electron. So, by the way, what electron configuration does this look like right now? 1s2, 2s2, 2p6. It looks like the electron configuration for neon. So we know that noble gases are stable because they have a full valence shell. And here it is. This is the argument that we made before. When sodium gets rid of this electron, the next inner shell here already has 8 valence electrons inside it. There they are. Or here they are here if I look at electron configuration. 2 plus 6. Inside there is my valence shell. There are 8 valence electrons inside there. So sodium can become stable, can get a stable electron configuration if it gets rid of 1 electron. It becomes sodium plus 1 ion. Well, what happens to the fluorine? The fluorine now has an extra electron instead of missing one. So when fluorine becomes an ion, its electron configuration becomes 1s2, 2s2, 2p. And where does that extra electron go? Can it go in a 1s? Does it go in the 2s? No, it's got to go in here and fill the 2p. Becomes 2p6, and this makes the fluorine minus 1 ion. Fluorine has an extra electron, and when it's done, guess what? It turns out to have exactly the same electron configuration as our sodium does. So fluorine can get the electron configuration of a stable noble gas when it forms a compound by grabbing an extra electron. So we can use electron configuration when we're talking about ions. So what's the important thing to learn here? Valence electrons are always the outermost s and p electrons. I can't take a 3s and a 2p and make a valence shell, but I can take a 2s and a 2p to make a valence shell. All right, always the outermost. So let's try another example. What if I had an atom like calcium? Calcium has electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Well, first question is this. First question is how many valence electrons? Where are the valence electrons? Your answer? Right here. It's always the outermost s and p. Calcium has in group 2, so we know it's going to have 2 valence electrons. What charge is calcium going to become? Well, calcium is in group 2. We know it's going to become a +2 charge. How is it going to do that? Because it is going to lose its 2 valence electrons. In other words, it's going to lose the 2 electrons that are in the 4s. So one way you can start to predict which electrons are going to be lost is it's always going to be the valence electrons that are going to be lost. So calcium is going to want to lose 2 electrons to become the calcium plus 2 ion, which will have the electron configuration 1s2, 2s, that's an s2, sorry, 2s2, 2p6, 3s2, 3p6, all right? Okay, good. Okay, the next part along our journey here is to talk about some orbital filling rules, and there's a new way where we're going to write some electron configurations using what's called orbital notation. And these are all famous scientists that ended up making some kind of contribution or another to the concept of orbitals. Aufbau principle, which basically says electrons fill orbitals starting with the lowest energy first, which means we start filling orbitals in the 1s and then move on to higher and higher orbitals. Pauli exclusion principle is something we haven't talked about yet, and I'm going to talk about that next. So Pauli exclusion principle says this: a maximum of 2 electrons can occupy each orbital. So we already know that. We know that an s orbital can have 2 electrons, but they must have opposite spins. So let's talk about that a little bit. It turns out electrons are basically, we can visualize electrons as little spherical balls, but we can envision them as spinning on a specific axis. And electrons can either spin clockwise counterclockwise, which is drawn here, or electrons can spin um, clockwise. And this is just a way to kind of envision it happen. It's not that electrons are actually spinning, but they can be thought of as if they're spinning. So, and I never remember which one is which, but the Pauli exclusion principle basically says that electrons, let's say we have electrons, here's a 1s orbital. And we know that it can hold 2 electrons in here. Well, the 2 electrons that go in here can't have exactly the same spin. So what we do is we say that electrons can either have something known as spin up, or they can be spin down, right? So if I'm going to put 2 electrons inside this orbital, the electrons that go in here have to be opposite spins. So one of the electrons right here could be a spin up electron, and the other electron here can be a spin down electron. Now, the idea of Pauli exclusion principle is, I don't know, it's a really important thing, and believe me, I've studied chemistry for quite a long time in my life, but Pauli exclusion principle means a lot more when you've taken courses with a lot more math in it. And I don't mean to imply that we're not, but I'm just saying for an intro to chem course, Pauli exclusion principle, this concept is about as far into it as we get. So suffice it to say that every single orbital can't have 2 electrons with exactly the same spin. Let's go on to a p orbital. A p orbital has 3 different shapes. This is one of the 3 shapes, and we know that this shape can hold 2 electrons in it. It can have an electron there somewhere, let's say an electron there. Well, all the Pauli exclusion principle is saying is that the electrons can't be both spin up or both spin down. One of them has to be spin up, and one of them has to be spin down. And in fact, the other combinations of orbitals that go along with this orbital has an orbital there, an orbital there. Instead of drawing the dots for electrons, I'm just going to draw spin up and spin down arrows to represent the electrons and their spin. So a complete p orbital would have 3 sets of spin up electrons and 3 sets of spin down electrons. All right. So it's just a consequence of learning about the atoms that electrons actually have spin, and we have to represent them. So that's what Pauli exclusion principle means. So let me show you how this works. So let's say we have electron configuration for an atom. Let's say we're just going to start with the atom boron. And we already know electron configuration for boron is 1s2, 2s2, 2p1. But we can represent that in something called orbital notation. So I know that the 1s orbital, and sometimes you're either going to see a box drawn around this or a line. Boron has 3 orbitals, the 1s, the 2s, and the 2p. And it has 5 electrons total. Now, the 1s orbital has to have 2 electrons in it, but they have to be of opposite spin. So we're going to draw arrows up an arrow down. And I'm even going to take the simplification of drawing half of an arrow. The 2s orbital is filled, so it's going to have an up and a down orbital. But the p orbital is a little bit different. Remember, the p orbital has three parts. It's got an x part, that looks like the z, the x, and the y part. So instead of drawing one spot here for a p orbital, instead I'm going to draw three. And this could be the 2px, the 2py, and the 2pz. So boron has 5 electrons. I've already used up 4 of them. So the 5th electron for boron has to go in here as a spin up. All right. So going back to our little discussion here, Aufbau principle says electrons fill orbitals from lowest to highest. We've got that. We talked about Pauli exclusion principle, where basically electrons that are in the same orbital have to have opposite spins. But the next thing that comes in here is something called Hund's rule. Hund's rule says electrons are distributed in orbitals of identical energy. This would mean something like a p orbital, because the three parts of a p orbital, the x, the y, and the z, are all said to have the same energy. They're distributed in such a way as to give the maximum number of unpaired electrons. Okay, so here's what that means. Let's go back to our discussion. So here we are. Here's what we're talking about. We want to talk about what Hund's rule says. That was my dryer, and it just went off. So let's go to an atom, the next atom over from boron, which is carbon. Carbon is going to be 1s2, 2s2, 2p2. And this is where things get interesting, because carbon has 2 electrons in the 2p. Orbital notation, 1s, 2s, 1, 2, 3 is part of the 2p. So as we've seen before, the 1s and the 2s are filled, so I'm going to put electrons in there, spin up, spin down, spin up, spin down. Now, what do I do here? Boron had 1 electron in here as a spin up. So what do I do? Where does this extra electron go? Does it go in here as a spin down? It turns out, no. What Hund's rule says is I have to put an electron into each of these parts of the orbital first before I start pairing them. So instead of putting an electron and pairing this up, I'm not going to do that. Let me pause so I can erase it. Actually, I'm just going to erase it. And instead of putting the electron here as a spin down, I'm going to put the next electron into here as a spin up. So this is the correct electron or an orbital notation for carbon. All right, so let's keep going with this. Let's go to the next atom over after carbon, which is going to be nitrogen. So if I went to nitrogen, the 1s and the 2s are filled. So I have up, spin down, spin up, spin down. But now I have 3 electrons in here. As we saw before for carbon, carbon had an electron in each of the 2p's. Nitrogen puts the 3rd electron in here and fills this. So this verifies what's known as Hund's rule. Let's go back and look at Hund's rule again. So Hund's rule said electrons are distributed into orbitals of identical energy, that would be something like the p, in such a way as to give the maximum number of unpaired electrons. Maximum number of unpaired electrons. So what we've done here in nitrogen is give the maximum number of unpaired electrons for nitrogen. And only for the next atom after nitrogen, which is oxygen, do we start ending up pairing electrons again. So oxygen is 1s2, 2s2, 2p4. So let me pause and fill in. So oxygen is 1s and 2s are filled. So I have spin up, spin down, spin up, spin down. And now if I'm going to go back and write what I had for nitrogen, spin up, spin up, spin up. Now that I have this extra electron, now that I have all these with unpaired electrons, I have the maximum number of unpaired electrons. Now and only now can I start to pair an electron up. So oxygen ends up pairing this extra electron up. Okay, now I'm going to stop right now and kind of go a little bit ahead, because we know that atoms want to make bonds. And if you remember our little bonding rule, H, O, and C, we said that 1, 2, 3, 4, oxygen atoms always want to make 2 bonds. Well, if an oxygen atom is going to form an ionic compound, it's going to take 2 valence electrons. Well, where are they going to go, right? If an oxygen atom is going to take 2 valence electrons, where are they going to go? Well, you're probably looking like, well, it looks like I could put 1 here and I could put 1 there, and you're absolutely right. So oxygen atom could become stable by getting a full valence electron by taking 2 electrons. But let's go to the next atom available. The next atom after oxygen is fluorine. So fluorine's going to look a lot like oxygen, with the exception that it's going to have one more electron. So I have spin up, spin up, spin up, and then oxygen paired this one. Fluorine is going to pair this one. Guess what's going to happen? Neon is going to end up pairing this one. So this is how orbital notation works. We have to follow 3 sets of rules when we're actually writing orbital notations. We have to obey the Aufbau principle, which says we start from the lowest orbital and then work our way up. We have to do Pauli exclusion principle, which says electrons in the same orbital have to have opposite spins, and as well as Hund's rule, is where we have orbitals who have identical energy, and the only orbitals that are going to be like this are p orbitals or d orbitals and f orbitals. S orbitals don't factor into this. Sorry, yeah, they don't. We have to give a maximum number of unpaired electrons first before we start pairing electrons up. So we have to, Hund's rule favors unpaired first, then we end up pairing them up. And this allows us to write orbital notations. So if you look at orbital notations for all of the atoms in periods 1 and 2, we go from 1 electron unpaired to 2 electrons paired. So this is a pair of electrons, all right? Remember that term when we start talking about bonding, and the electrons are in here as spin up, spin down. And then we went through the complete succession of boron, carbon, nitrogen. So nitrogen has the max number of unpaired. I'm just going to write un right now, and going all the way up to neon. So electron configuration and orbital notation kind of give us beneficial information when we start talking about bonding. Okay, so now we're going to talk about the last sections of chapter 7, which is periodic properties. I'm going to go a little bit fast with this. Once we know electron configurations, we can start kind of thinking about how reactive atoms are. And we spent a little bit of time talking about this already, but I'm going to introduce a couple new terms. Ionization energy, which is basically how much energy it costs to lose an electrons, and atomic radius, and some trends dealing with these things. So we know that atoms get more reactive. If we look on the periodic table, the atoms that are the most reactive are in the first 2 groups, and they get more reactive going down. So we expect to see atoms down here like potassium, strontium, calcium, sodium as incredibly reactive, and atoms that are like maybe in some transition metals are less reactive. And this is something we've seen. We looked at activity series, and the more active a metal, the more easily it loses electrons. So we kind of already looked at reactivity. So to remember our reactivity series, this is going down the first column, first group, and we know that atoms get way more reactive. This is taking a chunk of lithium metal, sodium metal, potassium metal, and just putting into water. Lithium kind of fizzes around, sodium fizzes around a bit and then blows up and lights on fire. Potassium catches fire immediately. Rubidium and cesium are so incredibly reactive, they just explode on contact with water. And this is something we've seen before. In general, with metals, as you go down the periodic table, they get more reactive, right? It's not the same way for everything, but it is in general for metals. It's kind of a general trend. Okay, so metals are things that like to lose electrons. And a term we're going to talk about right now, which is known as ionization energy, is literally, it's a measure of the energy required to remove an electron. Remove not just any electron, but remove a valence electron from an atom. So an atom like magnesium is, I'm going to draw like the core here for magnesium, and this represents the valence shell. So this is the 3rd shell, or the 3s shell for magnesium. It's going to have 2 electrons in it somewhere. And we know that magnesium is going to want to lose electrons. Well, the first electron to be lost for magnesium is going to cost 738 kilojoules per mole of magnesium atoms. Rather, I should say the first mole of electrons to be lost from a mole of magnesium will cost this much in energy. So the farther, there's kind of a couple terms for ionization energy. In general, the farther away an electron is from a nucleus, the lower the ionization energy is. All right, so if I'm looking at an atom, and let's say here's the nucleus, and I have a shell here, and I have a shell all the way out here. This electron is held to the nucleus weaker than, let's say, this electron. So this atom out here is going to have a relatively low ionization energy, where the ionization energy for this electron in here is going to be huge. So the bigger the atom is, the electrons on the outside have relatively low ionization energies. Now here's kind of one way to look at this. If I've got an atom, here's my circle, that's not a terrible circle, and here's my nucleus. The nucleus is positive, and the electron out here is negative. Now, in physics, we know that these two things are attracting each other, right? And this is why electrons don't just fly away. It's because they are actually attracting each other. So the problem is, the farther away this electron is, the weaker the attraction actually is. So the weaker the attraction, the less energy it costs to remove the electron. So the weaker the attraction really is, the lower the ionization, how do I write this? Ionization energy. Right, I'm just going to write that I energy for ionization energy. So how do we know this? Generally, we know this with the farther the atom is away, the farther the electron is away from the atom. So even if you add an atom and a multi-shell or multi-orbital electron, as you go farther and farther and farther away from the nucleus, the electrons get harder to remove. But also, the larger the atom, the lower the ionization energy, the less energy it costs to remove. The one thing we know, there's another trend that deals with valence electrons. As you go from one valence electron over to 8 valence electrons, the ionization energy goes through the roof. So ionization energy increases dramatically as we go from 1 valence electron to 8 valence electrons, because an atom with 8 valence electrons is incredibly stable. And an atom with 8 valence electrons simply does not want to lose electrons. So one of the trends we see is ionization energy goes through the roof as we get to the point where we have 8 valence electrons. Okay, so here's a graph that shows ionization energy versus atomic number. So this is going from atom number hydrogen all the way over to atom number radon. And the thing we see is we go across the periodic table from hydrogen to helium, the ionization energy goes through the roof. What happens going from hydrogen to helium? Hydrogen has a configuration 1s1, helium is 1s2. So helium has a full valence shell. Look at this, its ionization energy shoots up. So the more full the valence shell is, the larger the ionization energy. So after helium, we go back to lithium. And we go lithium raised all the way down here. Lithium has two shells. Lithium has its 1s shell, and lithium has its 2s shell. And there's only one 2s electron. So this electron, this 1s shell is, by the way, is full, right? So it's really hard to remove electrons from here, but this 2s electron for lithium, and this is a lithium atom, is a lot farther from the nucleus. Not to mention, there's only one valence electron in it, so the ionization energy from lithium is really, really tiny, right? But as you build, as you go from lithium all the way across the period to neon, what you see is the ionization energy shooting up. The only difference between lithium and neon is neon has a full valence shell. In fact, if you go from the peak of every single one of these atoms, helium, neon, argon, krypton, xenon, radon, what are all those atoms? All those atoms are noble gases. Noble gases already have full valence shells. So we expect to see the noble gases with a peak in ionization energy. Those are the atoms that are hardest to remove. So not to mention, as we go across from lithium to neon, as you go across a period from one valence electron to 8 valence electrons, every single time you do this from one valence electron to 8, 1 valence to 8, 1 to 8, the ionization energy goes up because we're getting more and more full shell. Now the other thing you notice is even though we're going from 1 to 8 each time, the ionization energy is still dropping. All right, so why is that happening? So as we go farther and farther and farther away from the nucleus, what's happening as we go this way is the atoms are simply getting bigger. And the one thing we said is the farther it's a terrible shell, but the farther this electron, so let's imagine a radius. The farther this electron is away from the nucleus, the easier it is to remove. And that's essentially why this is saying this trend is decreasing downwards. Because what's happening as you're going this way is these atoms are huge. Cesium is gigantic compared to rubidium. So the electron in cesium, the outer shell electron in cesium is simply easier to remove than it is in the atoms that come before it. Okay, so ionization energy is a pretty interesting trend. It tells us how easy it is to remove an electron. And what it really does is kind of confirms some of our theories about how strongly held electrons are to an atom. So this is another graph, kind of a three-dimensional graph showing you exactly the same information. And we find over here, these elements over here are noble gases. These are the ones that have full shells. They have the highest ionization energies. It's the hardest to remove electrons. Our electrons over here only have one valence electron. So it's all very easy to remove one valence electron versus removing 8. So as you see going across, as you go from one valence electron over here to 8 valence electrons, it gets requires more and more energy to remove electrons. So here's just another graph showing that as the atom gets bigger, as the electron is farther and farther away, the ionization energy drops simply because the electron is farther and farther away from the nucleus. Okay, so for this next section, I kind of shaded out all the answers. So we want to know which of these has greater ionization energy, magnesium or calcium? Well, magnesium, calcium are right next to each other on the periodic table. Magnesium has one valence electron, calcium has two valence electrons. So which of these is going to have the greater ionization energy? Which one is going to be harder to remove an electron? Sorry, I totally screwed that up. Magnesium and calcium are not right next to each other. Magnesium is here and calcium is here. I have no idea what came over me. And not to mention, but they both have two valence electrons. Okay, so now, which one has a greater ionization energy? What happens as you go down the periodic table? Calcium is a huge atom compared to magnesium. So as the size of the atom increases, the ionization energy drops. So we would expect it to be more expensive. It would cost more in energy to remove an electron from magnesium than it would from calcium. Hopefully that makes sense. And there, I erased my answer. So now let me clear this up and look at the next one. Oxygen versus fluorine. So oxygen versus fluorine, where are oxygen and fluorine? Now, in this case, oxygen and fluorine are kind of right next to each other. We've got oxygen, nitrogen, fluorine, and then neon across period 2 of the periodic table. So oxygen versus fluorine. What happens as you go this way? We are getting more valence electrons. All right, we're getting more valence electrons. So we should expect fluorine to have a higher ionization energy than oxygen. And if we check our answer, we are correct. What about sulfur versus fluorine? Sulfur is a little bit tricky because sulfur is, if I've got, hold on, let me erase some stuff. So the next problem is looking at sulfur versus fluorine. Now sulfur is this atom here and fluorine is here. So in the last problem, we said fluorine is going to have a greater ionization energy than oxygen is because it has more valence electrons. Well, what about this? What's the difference between fluorine and sulfur? Well, sulfur is in the third period where fluorine is in the second. So this is a different situation. As you go from the second to the third, this atom is physically bigger. Fluorine is this, sulfur is going to be this. So we said the bigger the atom, as we go from the larger the atom, the ionization energy is going to drop. Bigger the atom, the ionization energy is going to drop. So we should expect to have fluorine still have the higher ionization energy. And there it is. All right, so hopefully this kind of made sense. So it's also possible for atoms to have more than one ionization energy. If you can imagine adding so much energy to an atom that it removes all of its electrons. Take, for example, lithium. Lithium has 3 electrons to start with. To remove the outside electron, this is the outside electron, it only costs a little bit of energy. Imagine lithium's electron configuration. Lithium is 1s2, 2s1. So this is the very first electron to get removed. It only has one valence electron. It doesn't cost that much in energy, but look what happens when you start to remove this electron. If I draw the orbital notation, I get 1s and then I get 2s. So there it is, one spin up, spin down. So the first electron to get removed is this one. This one costs us 520 kilojoules per mole to remove. But the next electron to get removed is this one. Now we're trying to break apart a full shell, and the energy like almost it goes up by a factor more. It goes up in more than a factor of 10. Is that right? Well, pretty close to, yeah, more than a factor of 10 to remove this electron, and to remove the next electron costs even more. So as we're going this way across in ionization energy, we're actually working backwards. We're starting from the outside electron and working our way in. So as we get into, by the way, anything that's in here is what's known as a core electron. If I have an atom like lithium, lithium has two shells. It has electrons here and here. The electrons on the outside are the valence electrons. The electrons on the inside are what's known as the core electrons. So no matter what, we always find out that core electrons require massive amounts of energy. Okay, so instead of just one ionization, I can have first, second, third, fourth, sixth, seventh, 10th ionization for atoms. So we can see it costs more and more energy to remove electrons closer to the nucleus, because electrons closer to the nucleus are more strongly held to the nucleus. Okay, so the very last trend we have to talk about is atomic size. This is also often known as atomic radius, and basically we take two atoms. It's kind of defined as taking two atoms and basically half the distance between the centers is what's known as the radius of two atoms. It's hard to take a single atom and actually determine what its radius it is, but if we take two atoms that are bonded to each other, the radius, in this case of chlorine, is going to be 99.5 picometers. And remember, 99.5 picometers is, to get that into meters, we put times 10 to the negative 12 on it. So the radius of an atom, like a chlorine atom, is really pretty small. Well, there's a trend. There's a relationship between the radius of an atom and its position on the periodic table. And this is one of the first things we saw way back when we looked at the periodic table card activity. As you go down, no matter what on the periodic table, the atoms get bigger. The the atomic radius increases going down because the electrons are simply, basically you're getting more and more shells. As you go down, you basically gain one more shell. This is 2 shells, 3 shells, 4 shells, 5, 6, 7 shells. So the atom has to get bigger. But we also saw going left to right, the atoms get smaller. And one way to think about that is as you get more and more electrons, we go from 1 valence electron here to 8 valence electrons, the atom gets more compact, right? So that's about as far as I want to go into that argument right now. Really what's happening as the atom gets more electrons, it's also getting more protons. So an atom, like the difference between something like nitrogen versus oxygen is nitrogen has 7 protons sitting here in the nucleus, a positive 7 charge. But it also has out here, its electrons, it has a negative 7 charge. So in physics, the equation which describes the force of attraction between the electrons and the protons looks like this. The force is relatively equal to the size of the charges divided by how far they are apart. So Q is basically how big this charge is. And the bigger the number that you put in here, the larger the force is going to go up. So as the charge increases, the force on the atoms increase. Okay, so that's kind of why what happens is, so as the force, basically as this force of attraction gets larger, the atoms get pulled together. As you go across from nitrogen to oxygen to fluorine, you go from +7 to +8 to +9 with fluorine. The larger that Q gets, the larger the force gets. So as the force gets higher, it essentially pulls the radius of the atom decreases because it's pulling the atom in tighter and tighter and tighter. So I hope that analogy made sense. So here's the same activity again. Magnesium and calcium. So magnesium is directly above calcium. Which one do we expect to have the largest atomic radius? Well, we're going down the periodic table, so it has to be calcium at this point. So oxygen versus fluorine, oxygen, nitrogen, fluorine. As you go across the periodic table, the radius has to drop. So we expect oxygen to have the larger radius than fluorine does. Yeah, I think they made an error here. I think when they made this, they made a bit of an error. Okay, so oxygen has to have a larger radius than fluorine, and then sulfur versus fluorine. We go oxygen, nitrogen, fluorine. Sulfur is beneath here, so we're looking at sulfur versus fluorine. What we know as we go this way, we get smaller, right? But as we go down, we get bigger, so we expect the answer here had better be sulfur for the bigger atom. And yeah, I think they made a mistake there again. I think what they did is they just copied. So this answer is incorrect, as is the answer above. So hopefully you will forgive McGraw-Hill Connect for making incorrect answers. Anyways, let's move on. Okay, this is the very last thing we're going to talk about. What happens is with ions. Ions, as you know, are things that gain or lose electrons, and something weird happens. If you take an atom like lithium, we know lithium is a metal with one valence electron that is going to want to lose. When it loses the electron, it gets smaller. So when atoms lose electrons, if you lose an electron, you end up getting smaller. So a lithium ion is tiny compared to the lithium atom. But if the atom gains an electron, which is what happens down here with fluorine, fluorine gains an electron, becomes bigger, right? So that's the last thing we're going to remember. Okay, so that is it. This is the end of chapter 7. So if I said that incorrectly in the past 2 videos, I'm very sorry. I'm also very, very sorry that this video was so long. Unfortunately, it's the way it's got to work. But anyways, um, watch the videos, read the textbook, do the homework, and ask me questions. If you have questions on this stuff, don't wait to do this. All right, don't wait. This stuff piles up. I looked for last week, and the small section of the lecture I gave for last week, I had only 5 people attempt the homework for chapter 6. All right, after the entire week, only 5. I know everybody's busy. I know you got a lot going on, but try to stay on top of this. Ask me questions. If you need help,